Welcome to the Future of C Code Review. My name is Robert Secord. I'm a technical director at NCC Group, where I develop and deliver secure coding training classes in Java, C, C++, and C Sharp. I do a lot of code security review type UDO work, and I'm the research lead for WG3, which researches reducing vulnerabilities at scale in open source software. I'm also a long-time member of the C Standards Committee. So we're going to start by talking about optimizations. Increasingly, compiler writers are taking advantage of undefined behaviors in the C and C++ programming languages to make your code faster. But these optimizations can interfere with the ability of developers to perform cause-effect analysis on their code. In other words, to understand what code is actually there, which code is being removed, how that code is being changed, and what the possible consequences of those changes on downstream results might be. So these optimizations increasingly are eliminating causality in software and increasing the possibility of software faults, defects, and subsequent vulnerabilities arising from those defects. So undefined behavior in C and C++ is not all that well understood. Basically, when a compiler encounters undefined behavior, it can ignore that completely with unpredictable results. In the C Standards Committee, they tend to say the compiler is free to go off and play the game of life. I think I've heard other people talk about nasal demons. So the compiler can also behave in a documented manner characteristic of the environment, with or without issuing a diagnostic, but that might include things like trapping or crashing in some manner. Or best case, it could terminate a translation or execution with a diagnostic. So the basic design of a optimizer for C is largely the same as an optimizer for any other procedural language. The fundamental principle is to replace computations with more efficient methods that produce the same result. So optimization might be based on pointer provenance-based alias analysis, and these optimizations can modify the behavior of code which has worked for some time, but which has these undefined behaviors. So there's three basic strategies that compilers use. One is called the hardware behavior model, where the compiler basically just generates the assembly code corresponding to the C source code, and then it lets the hardware do whatever the hardware does. That's sort of been the nearly universal policy for many years. So folks who have been programming in C and C++ for some time might just come to the conclusion that that's the way the C language works all the time. There's a super debug model where that basically provides a intensive debugging environment that will trap every undefined behavior. This is not meant for deployment. This will severely degrade the application's performance, so it's used as basically a debug and development tool. And finally, there's the total license model, where undefined behavior can be treated as a can't happen condition. And this model allows the compiler to optimize aggressively. So the semantics of pointers and objects has been unclear for many years and possibly always, but this came to light in the early 2000s when compiler writers were working with alias analysis to perform better optimizations. And so really understanding how point of provenance works is necessary to understand how a compiler might optimize your code. So we're going to demonstrate this with an example. So here we've got a very small function which declares two variables, y and x. And we then create two pointers. and P and Q, and X and Y might be allocated adjacent memory. And if they are, then we're assigning Q equal to the address of Y, but we're assigning P equal to the address of X plus 1. And so if Y is right after X in memory, there's a good chance that X plus 1 is the same address as the address of Y. And so what we do here is we do a mem compare to see if these two pointers are in fact bitwise equivalent, if they're exactly the same set of bits in each pointer, if they both reference the same address. And if they do, we're going to then write through pointer P the value 11 and then print out the result. And the question here is, does this code have undefined behavior or not, or can we, or does the standard require, what does the standard tell us what the output of this printf function must be? So there's quite a lot of variation between different compilers. So if you compile this, for example, with GCC, you'll get one set of output. If you use the Intel's compiler, you'll get a different output. And if you use Clang, again, you get completely different output again. So what's going on here is that there are different models which can be used to think about what that code means. The first is the concrete model. And in the concrete model, again, this is equivalent to the hardware model. The compiler generates the corresponding assembly code and just lets the hardware do whatever it is that the hardware does. This tends to expose the memory semantics of the underlying hardware. And so pointers are basically addresses, memory addresses that refer to a specific memory location, and that memory location may or may not contain an object. It doesn't really matter. It's just writing to that location in memory. So Clang outputs X equals 1, Y equals 11, star P equals 11, and star Q equals 11. And this is the what you would expect from an application of the concrete semantics. So the idea here is that this pointer P is pointing to the storage occupied by Y, and Q is a pointer to Y. So all three of these values, all three of these expressions produce the value 11. So looking at the code again, what you'll see is that P and Q again are going to refer to the same storage, the storage that's been initialized, the storage identified by Y, which has been initialized to 2. And so when we perform this write through P, we're going to change the value stored in Y, and this is also the value referenced by P and Q. So when we print out the results, we'll see that the value of Y is changed, and the value of star P has changed, the value of star Q has changed. All three of those have changed. X has not been written to, so X remains the same. The other model is the abstract model. So in the abstract model, the language types enforce distinctions. So there are distinctions between numeric types that support arithmetic, and pointer types that support dereferencing. So this allows the implementation to treat any possible undefined behavior as a can't happen condition and aggressively optimize your code. So the compiler can also reason about the provenance of pointers, basically think about where the pointers come from. So a pointer which points, if a pointer points to a particular object, it can only point to that object. It can't be changed to point to a different object. That would be undefined behavior. And so in particular, these compilers rely on alias analysis to deduce that two pointer values might not refer to the same object. So GCC is an example of a compiler that applies this abstract model. And the result is you get a very different output from that code. Instead of printing out y and star p and star q equals 11, it just it says y is 2, q, which is a pointer to y, also still has a value 2, and the only value that's changed is expression star p. And so what's going on here is the compiler is reasoning that star p does not alias with y or star q, and consequently those values, the initial value of y equals 2 is propagated to the printf statement. So if we look back at the code again, you'll see what happens here is that, again, we're adding the address of x plus 1, and we're assuming that address now points to the same storage as y. And this is not undefined behavior because we're forming what's referred to as the too far pointer. It points to the the next element in the array following the first element, and you can think of a scalar as a one element array. And so so this is supposed to be this pointer p is pointing to x, although the pointer is pointing to the too far element, not to the actual storage for x. So and q is initialized to point to y. And so both of these pointers, p and q, now have provenance. P is a pointer to object x, and q is a pointer to object y. And once the provenance is established, it can't be changed. So down here in this code, when we make the assignment through p, we're only modifying p. We're not modifying y because p is not a pointer to y. And in fact, we're not even modifying x because this pointer's been changed to not reference the storage for x anymore. So when we print out the results, the compiler reasons that the only thing that's been changed is this expression star p, and it's been modified with the value 11, but all the other L values here retain the original value. So of course, there must be undefined behavior going on. If we're getting different results on different implementations, clearly the standard has not defined what the semantics of that code is. So the undefined behavior in particular is from section 656 of the C standard. And it says that if both the pointer operand and the result point to elements of the same object, this is the result of adding a pointer to an integer, or one past the last element of the array object, which is the too far pointer, the evaluation doesn't produce an overflow. Otherwise, the behavior is undefined. So in our example, we only point to the too far, so this behavior is defined. If the result points one past the last element to this too far pointer, it can't be dereferenced. And so when we dereference p to assign it the value 11, that is undefined behavior according to the C standard. And so here's Agnes Harkness saying, it was undefined behavior all along. So this was actually handled in a defect report all the way back in 2004 to the C committee. This is when compiler writers were working on alias analysis and realized that they needed to keep track of the provenance of pointers and that this was going to affect the behavior of the code. So the committee responded to this defect report. The implementations are permitted to track the origins of a bit pattern, and they can treat pointers based on different origins as distinct, even if those pointers are bitwise identical. So the kind of shortcoming of this is that this committee response to this defect report has never made it into the standard. So the standard doesn't mention this at all. So you would have to point to the defect report to indicate the intent of the committee with respect to this behavior. So the committee is currently trying to rectify all of this. and there's a study group underway that's looking at the C memory model, and they're developing a draft technical specification called a Provenance-aware memory model for C. Here are some of the members, the authors of this technical draft, and members of this study group. You can see we've cited a fairly recent document here, and you can find this on the WG14 website. If you want to read it, it's well over 90 pages in length. But what this proposal says is that each abstract machine pointer value is a pairing of a concrete address with a unique ID for each object instance. And this applies to static, thread, automatic, and allocated storage duration, or an empty provenance. And so the provenance is preserved by pointer arithmetic that either adds or subtracts an integer to a pointer. So like you saw in our example, adding 1 to the address of X doesn't alter the provenance of that pointer. It will always continue to refer to the same object. So any access via the pointer value, the concrete address has to be consistent with its provenance. Otherwise, undefined behavior occurs. So basically that has to be a valid pointer that's pointing to that object. And in the case of an array, that pointer could point to different elements within the array. So the pointer could have different values, but still be a valid pointer and still refer to that array object. So the access via the pointer value, which has provenance, again, must point to the same object, and that object must be alive. The lifetime on that object must not have expired, for example, because it's an automatic variable and the function it's defined in has returned. So any other access, including those via pointer value with empty provenance, is going to be undefined behavior. So let's take a look at this with a graphic that should make it easier to understand. So before we access the value through the pointer P in our code example, basically the storage is configured like this. And so the first thing we have, let's start over here. We've got the object X, which is a signed integer, and we've given this an ID. So this has the ID of 5. So this is just a unique identifier for this object. And it's at a particular address, and we're going to say the address is hexadecimal 48. And you can see that X has a value. It's initialized to the value 1. Similarly, we have object Y, which is also assigned int. It's given another unique ID, which is 6 in this case, and it's got its own unique address. It's been initialized to the value 2. So then we declare pointer P, which is a signed int pointer. It has a unique ID, object ID, which is 7, and it's got a unique address where this pointer resides. And it's initialized to the value of X plus 1, which is actually going to refer to the storage allocated for Y. And we have Q, which has its own unique ID 8. It's also assigned integer pointer. It's at a unique address, which is 58. And so this Q is initialized to point to object 6, which is Y, and it contains an address which is for Charlie, which is the address of Y. And so you can see in this case that X has a pointer value that's sort of inconsistent with the object it's supposed to be referring to. And so when you attempt to access this object Y through P, you can see, or the compiler can see, this pointer value address is not within the storage instance of the ID 5 of this signed integer object X that it's supposed to be referring to, and consequently this this indirect read or write is considered undefined behavior. So in summary, the problem is that this code that we're looking at, this function, has had undefined behavior all along. That undefined behavior has been typically interpreted using this hardware behavior model, but that's not a requirement of the standard that it be interpreted in that manner. Compilers have been more aggressively optimizing. They're trying to do alias analysis to significantly improve the performance of C code. And as a consequence of that, they're looking at this code and they're compiling code that used to work with these optimizations. And in some cases, that can alter the behavior of that code and cause the code to now fail. So it's important that you recognize these undefined behaviors in the code. And in some cases, that code might, depending on how you compile it, what sort of optimizations are being used, that code might now produce a defective program. Or if it doesn't produce a defective program now, it might produce a defective program in the future as the compiler that customer is using implements these optimizations. So the C standard itself is a contract between compiler writers and programmers. This contract is being amended all the time at each meeting of the C standards committee. The decisions are made that are going to affect, basically the behavior of the language and what compilers can and cannot do. The WG14 membership consists primarily of compiler developers, and to this day, 2021, the evolution of the C language is still being driven by performance, and this is based on really the behaviors of the customers of these compilers who, sometimes don't like these optimizations, but are unwilling to sacrifice the performance gains that these optimizations provide. And so the compiler developers continue to more, pursue more and more aggressive optimizations. So unless more security conscious groups speak up and sort of speak up loudly in the context of the standards committee or in discussions with your compiler vendors, the continuing tendency is to actually eliminate guarantees from the standard to allow greater optimizations and subsequent performance improvements, but less guarantees about the correctness and the security of the code. So that's my talk. I can take any questions. I'm also available Twitter, LinkedIn, and here's my email at NCC Group. Thank you very much for listening to my talk, and let me know if you have any questions. Thank you.